It's my great pleasure to welcome our speaker, Max Simchowitz here. So Max has, well, as I sometimes say, a relatively short but a very, very spectacular CV. He did his bachelor in Princeton, and now he's a PhD student at UC Berkeley. And he has worked in many, many different topics and contributed fantastic scientific contributions all over the place, including topics in adaptive sampling, in optimization, non-convex optimization, and recently he's getting into, well, this world between reinforcement learning and control theory. And he's going to be presenting his most recent fantastic work on improper learning for non-stochastic control. So please, Max, the stage is yours.
Awesome. Thank you so much for the introduction, Gergely, and thanks, Chiara and Shaba, for having me today. Really excited. So today I'm going to present work called Improper Learning for Non-Stochastic Control. Both of those are kind of jargony phrases, but hopefully by the end of the talk, we'll understand what they mean and how they fit together. So again, I'm Max, I'm at UC Berkeley, and this is joint work with my collaborators Karan and Elad while I was visiting Princeton University. And this kind of is a continuation of some work that they have started. So I'm really indebted to their work. So today we're going to talk about control problems. Control problems are oh, can you still see? Sorry. Here we go. Control problems are kind of problems that are inspired from things in physics. So you might see this in the high school physics textbook. It's a cart pull diagram. And in a control problem, you have a state of the world. Think of it as the relative positions and velocities of all the objects in the scene. And the state of the world changes. So it changes according to what we call dynamics. And these would be specified by things like masses, lengths, and the constant of gravity. Now, in addition to the dynamics that we plan for, we also have those that we don't. We have things like disturbances that affect the state of the system, things like wind or gravel on the ground. And in this entire system, our goal is to make the system do something, elicit a desired behavior. For example, how do we ensure that the mass maintains a certain angle theta with the vertical? And the way we do that is we input something into the system. We apply a control input. In this case, we'd apply a force to tag the cart along, allowing the mass to stay upright. So even though I gave you a very toy example, control is actually useful in kind of much more interesting settings than this. Maybe the big classical success of control is airplanes. Airplanes you can often fly off without having test flown them. And this is because we kind of understand the control theory so well that we're guaranteed that they're going to fly in most cases. Recently, we've become really interested in autonomous vehicles, so self-driving cars, unmanned aerial aircraft, and controls being used to great effect in these settings as well. Industrial robotics is also really cool. We're trying to get robots to do ever more complicated tasks, and control is really important in these areas. And then lastly, there are kind of non-mechanical problems that also use tools for control theory. So things like distributed server cooling or things like power generation and smart grid also use tools for control. So kind of as a point of departure, I want to explain the LQR problem. This is kind of like the simplest problem in control, and it's kind of the foundation also for the learning theoretic work that we've been doing. So in the LQR problem, I have a state that's evolving in time. And I'm going to note that my state's by bold letter X. And we're going to assume that the state evolves linearly. So as a linear function of the past state, and also linear in the control input to the system. There's also going to be some Gaussian process noise, which is going to affect the evolution of the system as well. And our goal is to learn what we call a policy, a control policy. And all this is something that tells us, given what we've seen so far, what do we do next, right? So given past states that we've seen and past inputs that we've played, what's the next thing for us to do? Now, in the LQR problem, our goal is to solve the following optimization problem, where we want to find a policy that minimizes what we call the cost functional. So what is the cost functional? In LQR, the cost functional is defined as a sum of quadratic costs of both the state and of the input. The intuition here is that I want my state to be small. For example, I don't want to be spinning off a racetrack. And I want my input to be small. For example, I don't want to have to apply too much force to do so. And this is really kind of a central problem in both classical and modern control techniques. So modern techniques use LQR in an iterative way to kind of locally represent a dynamical system and solve kind of optimal control locally. So it's also very well understood. In 1962, Kalman showed in a seminal work that the optimal policy, the right thing to do, is actually quite simple. It's just to play inputs that are linear functions of the state. And this linear function is given by some matrix. And this matrix solves kind of a well-studied mathematical equation, the discrete algebraic Riccati equation. So the thing that we should take away from this is that LQR, as stated, is really well studied and very well understood. So now I want to move to a kind of learning theoretic variant of the online LQR problem that's been studied in recent years by our community. So again, we have the same dynamics and we have the same objective. But the key difference in online LQR is that we start with an unknown system and we need to learn it. So here our goal is what we call regret. And regret means you consider some adaptive algorithm that's trying to learn the dynamics on the fly and use those to control the system. And you compare it with the optimal policy for known A and B. For simplicity, we'll take it in expectation. So here we have to kind of balance our exploitation of our knowledge of the right controller with our exploration of what the system is. And one way to think of regret is as sort of comparing to the best in hindsight. So if at the end of the game I see, oh, this is what my system looked like, how well did I do without that foreknowledge? So actually, we're kind of indebted to one of the organizers of this talk for popularizing this problem, Shaba, and his, at the time, student, Yasin, in 2011, were kind of the first to study the online LQR problem in this formulation. And then there's been tons of follow-up work as well. My colleague Sarah, lots of other groups at Berkeley, my colleague Horia, and then in some recent work, we did some lower and upper bounds for this problem as well. But for this talk, I want to explain how we go beyond the online LQR problem. And in particular, I'm going to focus on 3 generalizations that I think are really important if we want to move to kind of richer control settings. So the first generalization for online LQR, we might think of as changing costs. So recall that in LQR, we had these fixed quadratic costs. The cost matrices stay the same at each time t. But there's actually very good reason to consider costs which do vary with time. And I want to motivate it with a simple example. So the reason that we're going to do this is we're going to allow our system to be kind of directed to doing kind of more interesting or richer behavior. So for example, consider a car on a racetrack. And suppose that I want to follow this really terribly drawn trajectory in white that would probably actually kill you if you tried to follow. But if I wanted to make my race car follow that trajectory, I could enforce that with some kind of loss function. So I could let the waypoints along this trajectory be vectors bold AT. And I could say I want my car to essentially have a state which is close to these waypoints, and maybe also penalize, for example, how much force I need to apply to stay to those. So we call this a tracking cost, and we can see that it's kind of far more expressive than the fixed costs that we get in the online LQR problem. In addition to this, there are certain things that we might want to do with constraints. So, you don't want to fall off the racetrack, then you're going to have a pretty bad time. And it turns out that non-quadratic costs, so even more general than this tracking cost, are very useful to understanding how to enforce constraints and control problems. So again, just changing costs are kind of a really powerful and important generalization for richer tasks. So now the second generalization that we want to understand is non-stochastic noise. So if we recall the LQR dynamics, our noise variable, the bold W, this was assumed to be Gaussian. But it's a pretty strong modeling assumption, and there's no reason that that should hold in general. So what we can do is we can assume that the noise really doesn't follow any model at all. And kind of mathematically what that means is sort of we imagine some adversary that's trying to mess with us. And we say the adversary, or kind of we think of it as nature, is allowed to pick these noises in whatever fashion they'd like. And this is gives you much more flexibility in what kind of things you can model, and also kind of how robust you are to your modeling specifications. And it's also related to other ideas in robust control. For example, something called H-infinity control. So the final generalization that we want to understand is partial observation, right? So we've got our changing costs, we've got our adversarial noise, and in partial observation, I don't get to see the full state at any time. All I see is a measurement. C is some matrix, think of it as kind of a short and wide matrix, and E is some additional noise. So I'm getting a noisy and low rank observation of the state of the system. I'm going to refer to bold Y as the output of the system, and this is going to be the only thing that we assume that the system can see. And the important point about this is that this gets us towards more realistic sensor models where we don't have full state information. In fact, most realistic sensor models are even nonlinear, and I have some future work with collaborators at Microsoft Research that tries to understand this case as well. So there's been tons and tons of work in these various settings, and they've all kind of addressed them in different ways and somewhat ad hoc ways. But what I want to ask in this talk is, can we unify these three generalizations into kind of one framework, and can we do them all at the same time? And where a lot of us here are learning theorists, so what we also want to understand is, do we suffer from trying to tackle this problem at a very high level of generality and with accommodating all these various generalizations? So kind of spoiler alert, actually we don't seem to suffer that much, and that's going to be sort of the main takeaways from this talk, is that we can kind of do it all at once. So I want to go into specifying exactly what problem we're trying to solve. So again, we have our dynamics, linear dynamics with some noise, and linear observations. And we define this as the non-stochastic control problem, and it evolves in the following fashion. So we have time steps t going forward, and at each time step t, nature selects some noise into the system. Now, as nature selects noise, we're going to assume that the noise is bounded for simplicity. So now the agent observes the output of the system. That's all the agent sees at this time. And the agent uses the output and the history to select the input. So again, this is based on observable history. This is everything in the past that's either an input or an output. We don't get to see the state. We don't get to see the noise necessarily. And then finally, after selecting the input for a given observation, the agent suffers a cost. And now our cost functional is defined as follows. For every policy pi, what we do is we look at the sequence that would have arisen under policy pi for the given noises that were realized by nature over the course of the game. So nature is going to have selected some noises, and we see what we would have done. So importantly, this is a counterfactual notion of performance. To reason about the cost for different policies pi, we have to worry about other worlds in which we'd done something different and potentially visited different states and had different outputs as a consequence.
Max,
right? Yes?
can I ask a question?
Sure.
Wasn't a previous slide cost dependent on the state?
Yes, so that's an important thing, and I'm going to get to that right over here.
Okay, yeah.
So we are assuming that costs are functions of y and u. The reason for this is that we can't necessarily, if you're in an adversarial model, you can't necessarily see the state. But what we can do is we can generalize to functions which are histories of outputs. So there's certain state-like variables. For example, if you want to recover a cost on position from a cost on velocity, or sorry, a cost on velocity from position, you could do that by using histories of y's to build in state-like costs. For example, you could make a Kalman filter and you could use that to recover an approximate state and put a cost on that. So we can't do exact costs on that. That just seems to be unidentifiable on the state, but we can have kind of very rich cost functions that would capture state-like costs as well. And of course, our results specialize to the model where you see the state as well.
So staying with your example of velocity and position, wouldn't it be the general case when you observe, oh, I guess you observe position, that's what you're saying.
And cost could be yt minus 1, let's say, and that gives you the state, that gives you a velocity, which you can have a cost on. Yeah.
Which is like potentially you're adding a lot of noise there, right? Like if you had noisy observations, then you're differentiating on the noise.
Yes.
Not really.
So you could also have costs which are, for example, a Kalman filter that's a bit less noisy, and you could encode a Kalman filter as a history of y's, and you could have cost functions that try to do the correct filtering of the state. Right. Yeah. Cool. But yeah, so I think that's actually an interesting point, that understanding, if we wanted to actually go after state costs directly rather than say, oh, this is a generalization, understanding how that end-to-end bound would be very interesting.
Okay.
Cool. So now I want to ask, what are we trying to do? So I gave you a cost, right? We're machine learning people. We like to minimize costs. So what are we going to try to do with the cost? Well, one thing we could try to do is online optimal control. So what optimal control means is you take the cost of the algorithm and you compare it to the exact optimal policy that you can do in hindsight, for every possible policy that you could try to do, right? And we could try to ask, is there a way to make these small? Roughly speaking, is there a way to make our cost of our algorithm not much worse than the best thing we could have done if we knew everything that we should have done? So it turns out we call this competing with optimal control. And by competing, we're going to refer to cases where I have something that I actually do and kind of something that I'm trying to do as well as. And having the difference be small, I'll call that competing. So it turns out this is actually way too hard for us to do, and most people that with kind of an RL background will kind of understand why. So the first problem is that it's just hard to do this online. There's sort of too much variability in how nature can select the noise to come up with an algorithm that can adapt to every possible realization of it, comparing to every possible policy. This is just way too strong. And it's also difficult for computational reasons. So if you start having non-quadratic losses, coming up with the optimal sequence of inputs just becomes a kind of an LP with exponentially many faces. And also you run into issues of POM-DP control because you're doing partial observability. So optimal control would be great, but it's too strong for us. I think in this sense, non-stochastic control is harder than online LQR. If we're talking about competing with an optimal policy, we're actually suffering a lot for our generality. So instead, I'm going to propose a notion of regret, and this was introduced by Agrawal et al. And Elad's group at Princeton for this problem. So here what I'm going to do is, rather than competing with every policy, I'm just going to compete with a restricted benchmark. And this is going to be a benchmark that's reasonable and sufficiently expressive. So just to clarify, essentially what we're saying is that we want our algorithm to do just as well as this best policy in big pi, what we call the policy or benchmark class, and do this in hindsight. So for every sequence of noises that nature could select, we compete with the best thing in hindsight, looking back at that sequence of noises, and also give a knowledge of the system. Simplicity, I'm going to drop the dependence on the noise and regret, just makes the notation a bit easier. So now we should just ask, what is our benchmark class? What are the policies we compete with? So in this talk, we're going to compete with stabilizing linear time invariant dynamic controllers. It's a bit of a mouthful, but essentially what they are, if you're not familiar with the control literature, they're just controllers whose dynamics or whose behavior kind of mirrors the image of the system that they're controlling. So specifically, these controllers take as inputs the output of the system, and the output of these controllers is the input fed to the system. So it kind of just flips things. And the dynamics of the controller are given by linear functions, and the controller has its own internal state, which we denote as. So these are the controllers we compete with. So why do we compete with them? Well, they're really the gold standard in linear control theory. So if you pop open most linear control, robust control textbooks, these are the sorts of controllers that people are considering. And in fact, in many cases, they are optimal. So for the LQR problem, this benchmark class includes the optimal controller. The way to see that is in the LQR problem, just your Y would be your X, and you would just ignore the A, B, and C matrices here, and then you would just get a linear relation between input and output. So they're a very rich class, and they're pretty useful. They're also optimal in more general problems tailored for partial observation, H2 or LQG, and optimal for certain robust problems like H infinity. So this is kind of, we're not trying to make up a benchmark class, we're really trying to borrow it from kind of years and years of control theory and kind of do well on their own terms. The other thing that we can do, and if we have time in the talk, we'll get to see a little bit of this, is we can also compete with some controllers that have nonlinear structure. And I think that's pretty cool as well. So we'll see that, we'll see a glimpse of that later on. So just to reiterate, this is our non-stochastic control problem. We have our linear dynamics, our linear observation. We have our protocol where nature selects noise. The agent sees something, figures out what to do, and suffers a cost. And again, our benchmark of performance is regret. So just for those that aren't very familiar with regret-like costs, essentially good regret means regret that scales sublinearly in the time horizon t. Intuitively, the cost typically will grow as linearly in t. So if the regret is growing sublinearly in t, then the regret is second order to the cost. And the first order, this and this are basically the same. Now I'm going to redefine the word optimal for the rest of the talk. And I'm going to say optimal no longer means competing with the optimal controller. It means optimal regret in the following sense. So it means that I'm getting the smallest possible scaling of the regret in t. There are going to be other factors, log factors, dimension factors. We're not going to talk about that in the talk, and where we don't think that we're optimal in these other factors as well. Okay, so now that we understand the problem, I kind of want to get into the results. And these are the things that we show. So again, we have our cost functional, we have our regret definition. And our first set of results is the following. We have an efficient algorithm. It's basically just based on gradient descent, and it attains the following regret. So if I know the dynamics of the system, I can get regret that scales as the square root of the time horizon. And if I don't know the dynamics, I can get regret that scales as the time horizon to the 2/3 power. So it's a little bit larger, but still sublinear in t. This is a pretty general result. So arbitrary convex costs, arbitrary sequences of noise, and the system itself doesn't need to be stable. All we need is access to a stabilizing controller, which is pretty cool. In particular, this bound is optimal, and the way to see this is kind of by standard lower bounds in online learning community. We don't know if this is optimal yet, and it's pretty exciting to understand. And also, of course, I'm hiding log factors everywhere. I just want to mention that these results on their own really are just generalizing past work to partial observation. So results were known in these kind of regimes. This is almost simultaneous work done by Elad's group just right before. This was in kind of earlier ICML paper from last year, and we're just generalizing these to partial observation, though the analysis for the unknown system is quite a bit cleaner with our framework.
So Max, there are a couple of questions that people are asking on the chat. So one of the questions is, do you have any conditions in the matrices ABC?
Oh, yes. So the conditions on the matrices are that we have access to a stabilizing controller for these bounds. What this is that the matrix doesn't have to be stable, though for the purpose of this talk, I'll explain the stable case. All we need to know is have some controller that can stabilize the system.
Right, which is like an output feedback controller as well.
Exactly. It doesn't need to be static feedback, but it's some output feedback. And we can do this basically for any such stabilizing one. You just need one.
And it doesn't even have to be in the same controller class. It can be an arbitrary controller that is stabilizing.
It does need to be, I believe it needs to be a linear dynamic controller.
Oh, okay. That's obvious. Okay.
Yeah.
So the other question was whether you need to make assumptions about the cost sequences boundedness.
Yeah. Exactly. So we have some Lipschitz assumptions, and we assume that it has sub-quadratic growth. That can be by other growth.
Quadratic losses are not allowed, or
no,
is that just in?
No worse than quadratic growth.
No worse than quadratic.
You could do cubic growth, quartic growth, whatever you'd like. It's just for the analysis, we chose it to be easier. The difficulty is that you're doing a control problem, so you can't assume the losses are bounded everywhere. So we wanted a more reasonable condition that was a little bit looser. So
I guess that's why people are asking these questions too, because they're worried about that. Oh, the state blows up, and what happens?
Yeah, and we have our losses. We're very careful to accommodate for that. That's a good question. Thank you.
Yeah. There will be some questions about stability of matrix C, and but I guess stabilizing. You will explain these later.
Yeah, we're not going to spend too much time on stability for people that want to understand. I would direct you to reading the paper, and for a big discussion of how to handle various unstable systems, I'd say read Appendix C in the archive, and that should give it in a lot more detail. In this talk, I'm not going to spend too much time on the stability, but just suffice it to say that all we need is a stabilizing controller. And how we do that is explained at length in Appendix C of the paper. Okay, so the kind of results that excite me a bit more are what we call fast rates, or improved regret scaling. So for these faster rates, if we know the dynamics, we can get logarithmic regret. And if we don't know the dynamics, we can get square root t regret. And this is under a kind of a stronger regime. So we assume something called the semi-adversarial regime. So here the losses are not just convex, and they have the boundedness assumption that you guys were keen to ask about. They also are going to be strongly convex. And the noise is going to be, think of it as adversarial with a little bit of Gaussian, more generally kind of a non-degenerate covariance. And this you should think of as like a smoothed analysis setting. Okay, so it's kind of reasonable that the noise, it basically says that the noise has to be a little bit in every direction. And we can get faster rates in this setting. So why do we consider the semi-adversarial regime? Well, it's quite general, but it also encompasses the online LQR and the online LQG settings, LQG being kind of like a partially observed variant of LQR. So this really still captures everything that we have in the LQR problem. And in concurrent work with my colleague Dylan Foster at MIT, we showed that, in fact, even for online LQR, the square root t rate is the optimal thing you can do. So the takeaway from these faster rates is actually that we're paying very little cost for generality, right? Not only do we get small regret in these settings, but in fact, our regret rate can be just as well as, or just as small as the regret rates in the online LQR problem, which is pretty cool. So it really speaks to how little is lost using our approach.
So quick question. Are you going to talk about the algorithms underlying these theorems? Are they the same in particular?
So the algorithms are the same, yeah. So the algorithm, I'm not going to talk about this one. This algorithm is, we'll see this algorithm, the previous one. This is gradient descent with the square root t step size, and this is gradient descent with the 1/t step size. The algorithms are essentially identical.
Right.
Yeah,
Can you adapt the step size in?
Yep. I mean, it's just you go from the weakly convex to strongly convex step size, and you have to spend tens of pages on the analysis for this guy, but it's the same algorithm, yeah. And I'll explain, I'll have another slide about kind of how it's really the same algorithm in just a bit. What I want to mention though is I have some follow-up work. So I show that if you replace the gradient descent algorithm with a Newton step algorithm, you can actually get some of these results for purely adversarial noise under a caveat that the system can be stabilized by static feedback, which is true whenever the system is fully observed, but if it's not fully observed, it's not always true. And potentially other settings also work for this, but it relies on some tricky stuff in control theory. But kind of we can use, the framework's pretty modular, so you can replace kind of gradient descent with Newton and you can get other stuff. There's also other work by Anima's group at Caltech, and they show that you could get logarithmic regret for the pure LQG problem. The intuition here is that having both process and observation noise gives you lots of exploration. But what's cool is they also use our framework to prove this result. Kind of it's pretty exciting to see other people take this work and use it for future work. I just kind of want to summarize our results. We have a unified approach. It kind of generalizes and improves upon lots of the prior work. And it seems to be providing a scaffolding for future work on these online control problems, which I think is pretty exciting. And kind of the thing that excited me about this, and particularly the square root t rate, is that we're really getting very little cost for our generality. We're able to get some of the similar regret bounds that we could in these very simple settings, but using these very general techniques. Of course, all I've talked about and all I will talk about is upper bounds. Whether or not this is the right thing to do in practice and whether or not domain-specific knowledge helps you is still up in the air. And Elad's group at Princeton is doing a really good job benchmarking these different things so that we understand actually, what you should run. Okay. Other questions about the results? Cool. So I'll go on. So I explained what non-stochastic control is, hopefully, and I explained what we were able to do. So what is improper learning in non-stochastic control? So the central kind of object in our paper is what we call nature's whys. And we define nature's whys as a sequence of outputs that would have arisen if you did nothing to the system. So with zero input. So it turns out that the dynamics can be written in the following form. You have an affine term, which is what would happen if you did nothing. And the actual thing that you see is the affine term plus a linear combination of your inputs. So importantly, we're using what I might call an improper representation. Rather than representing the stepwise dynamics as the problem is specified, all we're doing is modeling the mapping between the inputs and the outputs. And this is in the spirit of lots of prediction algorithms where we really just focus on kind of a prediction or optimization task. Here, this matrix G, these are what we call the Markov parameters of the system. And we're not going to go into exactly what they are, but basically they're very easy to recover from the dynamics. And they're also very easy to learn from data. So they can be learned just directly by least squares in a very easy way without having to go through the A, B, C, D matrices. If we flip our equation around, we see something that's pretty interesting. It's that we can recover this counterfactual nature's whys just by looking at our input-output data. So if we just took our y, let's say for simplicity, we're going to assume we know the system right now, just for intuition, and we knew the Markov parameters. We could just subtract off inputs times Markov parameters, and we could get out what would have happened if I did nothing at all. And this is important because we don't need to see the state or the noise to do this. We just look at input-output data. So this is really the most important equation in the whole talk, because this talk facilitates us, the reasoning about other worlds, counterfactual situations, where we did nothing and then had zero input. And this is pretty important for the techniques. So again, these are counterfactuals, and they're very important in control because, again, our benchmark is sort of what would have happened if we had done different policies. Okay, so improper learning control, maybe it's best called convex parameterization, depending on who you ask, because in a lot of ways, there's sort of a one-to-one correspondence between the quote-unquote improper representations and the proper ones. So it's not clear exactly how improper it is, but you can call it either convex or improper. So we have our stepwise dynamics, and essentially we want to provide convex representations of them. So our stepwise dynamics, you have this kind of complicated recursion for our linear system as the state evolving in time, and your observations are linear in the state. And the convex representation is just the input-output map, right? So you have your nature's wise, you have your Markov parameters, and all you're doing is considering how inputs affect what you see. Now, similarly, we're going to do the same thing for the controller, and this is a bit less obvious. So we have our controller dynamics, again, this complicated recursion. But what we're going to do is we're going to represent them as well by a linear map and a linear map in nature's wise. And these are just linear combinations. So this is actually related to the Euler parameterization that we didn't realize it immediately at the time. But there's a long history of doing these convex representations in control, typically for computational purposes and for constraints. And this controller that we're going to see in the talk is the simplest version of the Euler parameterization. But for unstable systems, there are more interesting versions. And again, for the interested reader, I direct you to Appendix C of the archive version to understand how that works. So there are two key insights that allow us to leverage this kind of improper perspective on control for our regret bounds. The first is, if you view controllers and dynamics as affine functions, you can take online control and you can make it an online convex optimization problem. And we're going to see how that works. And this is an insight due to Agrawal and Elad, so we borrow it from them. Importantly here, convexity is being used for two purposes, both for the computational purpose, it makes it easy to run algorithms, but also it buys us some statistical efficiency as well, because online convex optimization is kind of easy to learn it. Now, the second insight is that the nature's wise parameterization, which is kind of the big observation of this work, and of course its generalizations, they allow us to handle partial observation in ways that weren't handled before. They actually make unknown systems very easy to handle, and they make getting our fast rates also like very reasonably clean to prove. And they also allow us to compete with dynamic controllers, which previous parameterizations were able to, but that observation wasn't really made. So this is kind of like the big new thing of our work, is having this perspective and its generalizations. Again, this is based, I need to credit Euler and Kucera a million times, their 1976 work, but there are some novel kind of control theoretic things that we do as well, again, in Appendix C. So in this talk, for the rest of it, I'm going to talk about a very, very basic case. We're going to talk about the known system dynamics and the stable system. But the techniques that we talk about are really going to underlie everything else that happens in the rest of the talk. So if you don't know the system dynamics, you want fast rates for unstable system, essentially this is still the platform that you use. You don't totally change the algorithm. So if I don't know the system dynamics, I use something called certainty equivalence. Basically, I just estimate the system dynamics with least squares, and then I put them into the system. And I basically run the same algorithm using my estimated version rather than the truth. And we call this improper certainty equivalence because I'm not trying to go after A, B, and C. I'm just estimating the Markov matrix G, which is kind of this convex representation. For fast rates, I run the same this is going to be a gradient descent algorithm. In fast rates, I just run the gradient descent with a correct step size. One key thing though is we actually have to use over-parameterization in our analysis. And so this kind of speaks to the theme of improper control, where over-parameterization is a big technique. But really fast rates are kind of this plus more complex analysis. Finally, for unstable systems, we assume access to a stabilizing controller, and we show that kind of morally all of the same parameterizations that we develop, they also work in this case as well, and they allow us to use the same techniques. So the technical work that accomplishes all these things is all in the paper. It's too long of a paper, and I don't have time to get to all of it in this. But kind of the important thing is that hopefully in the remaining time I can communicate the big conceptual ideas that allow us to springboard off and get these applications. Also, I want to mention again that in addition, this core algorithm is also sort of the platform for future ones in many ways. So really understanding this very simple case gives us the insights for the more interesting ones as well. So in the time I have remaining, I'm going to explain the two components of how we accomplish the very simple case of known system dynamics in a stable system. And the two are the nature's wise parameterization, which I've just explained, and we'll go into more detail in, and online convex optimization with memory. So this is how we pose our problem as some kind of convex learning problem. And this is how we solve the problem. And this OCO with memory, it's actually, these insights are due to Oren Anavan, a 2015 paper. Okay. So remaining bit of the talk, I'm going to explain kind of just how we solve this simple case, and the paper will explain how you kind of build off that for the more interesting versions. And stable systems. So I want to explain what it means to have convexity in a control system. So we remember we have our system dynamics, and we're being improper, so we're just viewing it as maps from inputs to outputs. Of course, the noise, and there should also be a bold E here, that affects the outputs we see. So now a controller says, I look at the output, I put it into some weird control box, and it spits out an input, and I feed this into the system. Control theorists call this closing the loop because the outputs of the system affect the inputs of the controller, affect the system, and so on in a recursive fashion. Now, we're going to say that a controller is convex if we look at the following counterfactuals. So we're going to parameterize convex controllers with letters M. Think of these as like vector-shaped objects. And we're going to consider the mapping from these vector-shaped objects to the outputs and inputs that would induce if we had run this policy. So in the other world where we ran this map, what would this look like? And we'll say that a controller is convex if this mapping is an affine one. So if you look at for every M, this mapping is an affine function in that M. And in particular, this is nice because it ensures various things that arise are convex functions. For example, the cost functional would be convex because it'll be a series of convex functions of affine functions, which are in turn convex. So this is kind of why we like these things. So let's understand why we can't just get convex parameterizations for free. So we could look at the feedback law, the static feedback law, and you could look at this and say, well, this is a linear function. This looks pretty convex to me. But it's not. And the reason is that the effect of the inputs of past inputs affect future inputs. So we get an effect called feedback, where this input here affects this output here and so on. And we have kind of a cyclic structure in our graph. And it turns out that this gives us a really highly nonlinear dependence on the matrix K, and it breaks convexity. And if you want to see this formally, you can see Mariam Faisal's work with her collaborators in 2018. So what we're going to try to do is we're going to try to write controllers in a different way, but that will execute the same behavior. But the parameterization will ensure that we get convex functions. So just to remind ourselves, we have our natures Ys. These are these things that we recover from input-output data. And importantly, they don't depend on what we do as a learner, right? They are the things that occur with zero input in some counterfactual law, or so counterfactual world where we just did absolutely nothing at all. Now, what we're going to do is we're going to observe the following. Because they exist in this counterfactual world, we can view them as the product of what we might call nature's dynamics, things that have nothing to do with our controller. Now, what we're going to try to do is we're going to use these as the basis for our control policy. So we're going to play control inputs, which are linear combinations of nature's Ys. Here, M is going to refer to sequences of matrices. Typically, we're only going to use them finite length, so they're going to be M plus 1 of these coefficients. And we're going to put nature's Ys through this M box, and it's going to give us this control UT. So again, for any M, we get this control. Now, we put UT into the system dynamics, and that would spit out what the output would be, again, in this other world where we play control M. Okay. So the important thing to realize is that, again, nature's Ys don't depend on the inputs to the system, and there's no feedback in how UT has been defined. So in particular, we also have linear maps. So as a function of M, this is a linear map, just by this definition. And this is an affine map because of the system dynamics being linear. So importantly, this setup gives us a convex controller parameterization, and it's because we've kind of made our control diagram look like a DAG, right? We've removed any cyclic structure from the graph. Another important thing is that I can also compute these counterfactuals. So using if I know the system for simplicity, and I can recover nature's Ys, I can understand what my controls would be under different M's, and I can compute what my outputs would have been under different M's as well. So this is important to reason about other situations. So, okay, I've given you a set of controllers. I told you that they have this convexity property. But the question is, why should we be using these controllers? Why should we be using these, what we call DRC controllers, or disturbance response controllers on the previous slide? Well, it turns out that they're very expressive. So what I mean by this is that if you take kind of a suitably parameterized set of these things, certain bounds and certain length little m, and you compare it to our benchmark class of policies, then the approximation error, it's linear in T, which seems pretty bad at first, but it degrades exponentially in M. And here we use the fact that these controllers are stabilizing. So what this means in particular is that if my little m is just a logarithmic factor, then I can make this distance just a constant that doesn't grow with my time horizon T. So in fact, even though they kind of look kind of funny, these controllers actually do compete with the best kind of iterative policies. And again, this is based on the EULA, observed by EULA. So just to have a little recap, sorry, did someone say something?
Yeah, just quickly asking a question. I think that we need to ask this question now. Like, what do you mean by stabilizing controllers? You mean just that the state and actions are kept bounded, or?
Yeah, so what I mean by this is that the state and the action, if you look at the closed loop system, where you've fed the controller into the policy, the state and the actions are kept bounded. So the controller doesn't need to be open loop stable. If you just put an arbitrary sequence, that could blow up. It just needs to be that together the whole system needs to be stable.
I'm just wondering about, like, how would you do trajectory tracking if the trajectory escapes to infinity?
So if this trajectory escapes to infinity, I mean, if this trajectory escapes to infinity, then you're kind of in unbounded territory. But if you're doing trajectory tracking, let's say on a ring, that's not so bad.
Right. Yeah, sure, I know, but like, okay.
I mean, you could probably do the system. Like if you wanted to have like a car going, through an environment, stabilizing controllers would still work. They would just you would just kind of have a moving affine term. I'm sure it would work out.
Yeah, I was just wondering how this all adds up with all the definitions. Yeah, like just imagine that. Yeah. Let me add one other thing. You can also compete with state controllers that have kind of DC or fixed output terms. So these might be more useful. It's pretty easy to show that you compete with these. So these might be more useful. So rather than just controllers that bring your system to 0, you could also compete with controllers that say fix your guy at a given point. Yeah, somehow I feel that like what's important for you is that somehow the costs are controlled.
Exactly.
Controllers.
Yeah, the costs are controlled. So you could probably use it like a recentering argument if you wanted to let the actual positions go. Yeah.
Yeah. Okay.
Well, that's a good point. Thank you. So just to recap, we have our natures Ys, or the things with 0 input. They give us our convex parameterization. They're expressive enough to compete with all controllers. We can recover natures Ys and compute counterfactuals of other things that we could have done. And it turns out when the system is stable, we have kind of stability of this. Roughly, this means that we can assume if we have a stable system that this mapping from inputs to outputs is Lipschitz and finite memory. If the system is not stable, but we have a stabilizing controller, we have the same property. So the important thing is that these parameterizations allow us to assume something like a finite memory property, depending on how things are configured. One thing I just want to mention is we've got some generalizations. So you can use things with nonlinear features. So you could play controls that are arbitrary nonlinear features of natures Ys. This would work just as fine. It doesn't really change the problem much. You could also have parameterize your controllers as affine terms times nonlinear terms. So for example, you could have something where mi of t is various kind of affine coefficients times, let's say, sines and cosines. So all these things can easily be accommodated, and they don't really change the algorithm or the analysis that much. And this is nice because in Elad's group, they like to kind of use neural networks to get some kind of control features and control based on those, and our algorithm can accommodate it. So just in the remaining time, I want to explain what the algorithm is. I've kind of done a lot of setup. I've explained what it means to be improper, but I want to just tell you the algorithm. I think I've been teasing at it for too long. So the algorithm is just gradient descent. So this is a simple algorithm due to Simchowitz in 2003. And the algorithm just says you take whatever parameter you have, you take a gradient step. The step size is 1 over square root t for this regime, but in strong convexity, this would be 1 over t. And you do a projection onto a constraint set. And the nice thing about this algorithm is that, at least for very basic regret, it's known to get square root t regret. So if I have an arbitrary sequence of loss functions and I run Simchowitz's algorithm on this sequence of loss functions, I get square root t regret, provided that my gradients aren't too huge, and provided that my diameter of my set isn't too big either. Okay. So importantly, for people that aren't super familiar with this kind of thing, you're not paying for the complexity of these functions, which can be arbitrary. You're really just paying for the complexity of the constraint set, cal m. So what is our algorithm? And it's actually quite similar to Agrawal et al. You just do gradient descent. So at each time t, you query your gradient descent algorithm for what your current control policy mt is. You then play the input, which would be parameterized by this. Remember, our inputs are just linear functions of natures Ys. And then you just create a loss function. So you say at time t, my nature reveals a loss. I know that I get some information. And I say my loss is just going to be what would have happened if I'd played different m's. And I feed this loss function to gradient descent. So again, the loss is the counterfactual that says, what would be my current loss if rather than doing what I've done this far, I just played online gradient descent as my algorithm. So again, you're using the DRC controller. These are the parameters being updated. So importantly, we know how to recover natures wise. We've kind of beat that horse already. We also know how to compute counterfactuals via the dynamics. We can compute what different inputs would do to the system using natures wise. So in particular, we can, this is an affine function, so this ensures that this loss is convex. So we're running gradient descent on convex losses. And it also ensures that our algorithm is executable, meaning that, at any given time t, we actually have all the information necessary to compute gradients and do the control problem. So that's pretty nice. So it's actually quite a simple algorithm. It's just basically you use gradient descent on kind of these counterfactual losses FTM. Now, here's even simpler, input and then gradient step. And our main theorem, just to reiterate, is that we get square root t regret. So if you look at the regret of our algorithm, the regret scales with like the square root of the time horizon t. Now, the proof of this, it showcases both our parameterization, how expressive it is, but it also showcases an idea called OCO with memory. So even though we're doing gradient descent on the losses that are pure counterfactuals, it turns out that our algorithm has to also pay for some memory term because we're in a control problem and past inputs affect future ones. So I don't have a ton of time, but I want to try to step through parts of the proof and explain how these arise. So the first part of the proof is to use expressivity of the DRC controllers to just say, rather than competing with big pi, I compete with my convex set M. And then what I do is I realize that, in fact, now that I'm competing with my convex set M, these are just by definition the loss functions FTM. So the right-hand side kind of looks like a standard regret problem that I'd like. Now what I'm going to do is I'm going to use stability to pretend that this matrix is 0 for all I greater than h. Again, if we have an unstable system that's stabilized by controller, we can similarly do the same kind of truncation. Importantly, we can then realize that the input of the algorithm, even without this restriction, is just UTMT. But the output of the algorithm is a little bit more sophisticated. So it's really kind of an input that's induced by a changing sequence of controllers that our algorithm has used. And this kind of is a challenge because it's not really clear that this is just some function of the current iterate. In particular, we have some function that has kind of memory h, where this just memory h is kind of coming from our truncation. So it depends on, this should really be an approximate sign, but we're making this very strong assumption for simplicity, and this is a function of kind of a couple steps back. So now what we want to do is we show that the regret, therefore, is of the following form. It's you sum over functions of the history, and you compare with functions that don't have history. And this framework is called online convex optimization with memory. I think it's really powerful. The key kind of relation between these two, of course, if these are unrelated to these and you can't really say anything at all, the key relation is that if I were to have the same parameter for every argument of big FT, I would recover little ft. So intuitively, if I play the same controller every time t, I would just have my counterfactual as if I played that controller. We call this the unary specialization relationship. It just means that if I use the same argument over and over again, I just get this guy back. And once I have this relationship, I can start to do pretty cool things. So it turns out that if I have this relationship, online gradient descent without modifications naturally gives me this nice regret bound. It's a strengthening of the Zinkevich bound, and because it allows for the effective memory. So what's going on here under the hood is that essentially gradient descent and most online learning algorithms are stable in a different sense. They change their iterates very slowly. So what this means is that, roughly speaking, this function looks like as if you just played big MT for all rounds. And this is what allows you to reduce to kind of a more standard regret problem. So I encourage you guys to read Oren Anava's paper if you want to see this in greater detail, or our paper. We also explain it as well. But it's pretty cool. You don't need to change the algorithm. It's just an effect in the analysis. And this is basically the rest. This just completes the proof. So we've just kind of gone step by step, reducing it to problems that we're more and more familiar with, and then we use this online convex optimization with memory machinery. So just taking a step back, essentially what we've been doing is what control theorists might call adaptive control, right? We don't know the noise distribution. We're kind of adapting to what's happened, doing the best in hindsight. And we've done this with techniques from online convex optimization. We've been using kind of the various nice properties of our parameterization. And it's a pretty easy algorithm. It's basically just gradient descent. And of course, if you want some more fun math in the paper, we have the sharper analysis with the stronger assumptions, but it's basically the same algorithm. It's just changing how we do the analysis. And that's what's kind of nice about these sorts of results, is that you show that very simple algorithms, if you study them carefully, can do really powerful things. And again, because we've kind of separated out the nature's whys and the optimization part, the framework becomes pretty modular. So again, we can switch out the parameterization for unstable systems. We can switch out the optimizer for different settings. We can estimate the dynamics and run the optimizer with estimated dynamics, and each part kind of functions independently of the other. So it's nice in that way as well. So I'm running out of time, and I want to kind of give my concluding thoughts on this work. So just kind of step back, what we try to do is we try to understand control with a regret benchmark, and in particular control that adapts to any particular noise sequence with these kind of changing costs and losses. We gave convex parameterizations, showing that these are really powerful tool to handle the problem at hand. We then used online convex optimization to facilitate learning in this problem. And we use also, this was an earlier iteration of the talk I didn't have time to talk about today, but the improper representations also let us learn dynamics very easily. And you can see this in the paper. We explain this there. And this is true even with adversarial noise, which is something I didn't get to mention, but we can estimate dynamics with adversarial noise. And there's some interesting connections to semi-parametric statistics, which you can look at in the paper. So one last thing, and this is again something that we didn't have time to talk about in this talk, but our ideas can be synthesized with with richer parameterizations from classical control to do kind of more general things, in particular dealing with the stable, unstable system business. So I think kind of stepping back even further, what's really exciting about this work, and I think a lot of the work that's been coming out of the RL and control communities and learning, is that we're taking ideas from learning theory and optimization, and we're mixing them with prior ideas that have been around for decades now in control and reinforcement learning. And it's really exciting to see the two communities getting to have more dialogue and seeing what kind of results come from their intersection. So that's the end of the talk. Thanks so much for having me. And I didn't have a finished slide, but I'm, I guess, ready for questions.
That's good enough for us, Max.
Okay.
Thanks. Thank you.
Okay.
Yeah, we do have a bunch of questions from the audience. So do you guys, Wouter, you had a question. Do you have a mic? I can hear something.
Yes, I do. Is it working?
Yeah.
Okay, great. So I was wondering, so you're using gradient descent on a representation that is sort of a sequence of matrices. I think you called them M.
Yes.
And I was wondering, like, what is the constraint set that you use for those sequences? And there is a projection step, and I'm wondering, is it itself then complicated? How does it work?
Okay, so for the theory, we wanted the cleanest theory. So we use something we call the L1 op norm, which is just the sum over L1 norm of operator norms of each coefficient. And the set is basically the set of all sequences of M plus 1 matrices that have this norm that's bounded. And we show that there's been there's a work that shows how to do projections on this, so we explain how to do it. In practice, you can just relax this and use the Frobenius norm constraint, and that would make the algorithm a little simpler. So in implementation, you should use Frobenius norm, but the theory, if you do the operator L1 operator norm, it helps us not have to carry around so many M factors, and it just cleaned up the math a little bit. But you can use Frobenius norm in the extended representation if you want.
So Max, are you saying that you get tighter bounds if you are using the L1 thing?
Yeah, I think we do. The bounds are only tighter by basically like the M parameter, which is really just a mixing parameter. But we do get tighter bounds. Intuitively, there's no reason to, if you have Frobenius norm, then you're kind of allowing like you're somehow like allowing the matrices to be large in directions that aren't that important. But if you have L1 op norm, you're really constraining kind of the total strength of the FIR in the norm that arises. I think that for LQR, if you have stochastic noise, Frobenius would make more sense because kind of like H infinity stuff or L1 would become L2 if you're in kind of a stochastic regime. But we didn't go into that too much. And it's really just stability parameters.
There was a related question earlier. I forgot whose question was it, but just let me ask quickly. How do you depend on dimensions and stuff like that?
So we're poly in dimension. We didn't try too hard to optimize over them. Let me look at the paper. Let me pull up my paper and see. It's not awful in dimension. The one thing that I do want to mention is that because we're doing non-stochastic control, you get this thing where you could imagine that the adversary. So our assumptions are on the L2 bounds of each of the different natures Y's. That's how we do our talk, or that's how we do our parameterization. You could also do it L1 bounds on the noises, or sorry, L2 bounds on the noises. And the problem with this is that the adversary could put all of the mass into like one coordinate, rather than putting the mass over all coordinates. And naturally, this can make the dimension dependence a little bit worse than what you could expect in other ones. But if you were to look at our, apply the algorithm to an LQR setting, what would you get? Well, you'd get kind of a certainty equivalence part where you're just learning the system, and the dynamics, the estimation rates for these are pretty well understood. And then you just run gradient descent, which on a strongly convex objective would probably converge pretty quickly. So we suspect that if you did a specialized analysis for kind of the LQR setting, the same algorithm would enjoy pretty near optimal dimension dependences as well. It's just that once we go to kind of adversarial noise, kind of power can concentrate in weird ways. And also, it's quite a long paper, so we wanted to kind of only really optimize for T. But that's an interesting question, and I don't think that if you had an LQR problem, this is the right algorithm to run necessarily if it's pure LQR. And in fact, in concurrent work, Dylan and I show that the right thing to do up to dimension and T is just kind of estimate the dynamics on the right basis and then control from there. In some sense, the estimation problem, and this is a little harder when you aren't guaranteed stochastic dynamics because you don't have unbiased noise. So you need to put input into the system, random input, to estimate it. And if you were in a stochastic regime, you could kind of let the system estimate itself. Actually, this is really interesting. This is how Anima's group, I saw him in the audience. His work that gets logarithmic regret, it uses the fact that in a partially observed setting, kind of you have enough stochastic noise, so you don't need to worry about a bunch of noise injection, and you can still learn consistently. So they're able to show for LQG, where you have observation and process, kind of having purely stochastic noise actually really does help you a lot. Anyway, that's kind of too long an answer. But the answer is probably not optimal in dimension. Yeah, but polynomial.
Yeah, so I have a question is that your regret bound heavily depends on the benchmark class you choose, right?
Yeah, so the benchmark class that we've chosen, the way that we parameterize it is we kind of say that they're strong stabilizing. So essentially we say we compete with all controllers, which ensure that the closed loop behavior has some kind of like H infinity norm, roughly speaking, or L1 norm, and that there's sufficient decay. So in particular, as you can always make the benchmark class bigger, you can consider sort of bigger sets of controllers, and you can consider ones that have slower decay. And that'll make the regret will degrade gracefully as those happen, right? So the regret will degrade sort of polynomially as you blow up the decay parameter and you blow up the magnitude. But yes, so the regret bounds very much depend on the fact that we've been using linear controllers to compare to. They can also work for those nonlinear controllers we compare to as well, so we can also put those in. But kind of general control classes we don't really know. Kind of just the motivation was this is what control theorists have been doing for decades, so why not try to compete with what they've been doing?
Okay, thanks.
Sure.
Yeah, so there seems to be a similar question posted in the chat by Diba Basu. I don't know, can you ask your question if you're here? or
Yep, thank
maybe
you.
just tell us if you're satisfied with this.
So specifically the assumption 4 that you have on the paper, like specifically the regret bound and the typical decay that you have assumed, can you explain under which kind of situations this will and will not hold? Like for
Yeah.
which kind of noise?
Yeah, sure. So yeah, exactly. So to make our results a bit more interpretable, we wanted to kind of give, in the paper, we wanted to give kind of typical scalings for various things. So if you look in Appendix A4, it explains sort of how the things arise, but let me give you a short answer. Essentially, the way we derive these scalings is we said, kind of roughly speaking, imagine that you had kind of Gaussian noise, maybe with some bias being put into your system. And you, how big would the various quantities be? So roughly speaking, if you have Gaussian noise in your system, why don't I try to share my screen for this so that I can point to what I'm talking about. So let me do that really quick. I'll just share my whole screen. Let's go to here. Present now, all window, and I think we should get. Okay, so can you see assumption 4 on my screen? Highlighted?
Yeah, yeah,
cool.
Yeah.
Awesome. So the D max maximum of noise, maximum of kind of input and output would be kind of the sort of it would be the kind of magnitude of the nature's wise that would occur if you just kind of put noise in every direction with the kind of the low rank observation that occurs from partial observation. The RG squared, this guy's coming from sort of how much the system amplifies noise. So typically if you kind of say that, you know, the system amplifies inputs at a certain rate, kind of in a general situation, it'll amplify noise at the same rate. You can always sort of inflate this parameter to make this the case. The sigma noise squared is just how big your noise is. And of course, this is kind of a high probability and uniform over T parameter. So this is kind of the rate, this is kind of the regime that you would get. Now the decay parameter is basically just saying that in general, if you have a stabilized system, stabilized systems decay geometrically. And you can make this quantitative. So I think some of the first work that did this in our community is Elad Cohen and Tomer Karan, and their work introduced a notion called strong stability. And essentially you can verify this by looking at certain Lyapunov functions for LQR. So even if you're not doing an LQR problem, you can actually use machinery from LQR and other Lyapunov function machinery to prove geometric decay. So this is kind of, I think, perhaps we should add a citation for their work for this latter geometric decay, but it's something that occurs in various systems. Is that
okay? Yep.
Cool? And again, just I want to reiterate that this is sort of typical scalings. So our regret bounds don't use assumption 4. They're just like the sentence that comes at the end of each theorem says, in particular, under assumption 4. This is kind of what you would see. Yeah.
I see.
Yeah. So it's just
yeah. That makes more sense.
Yeah,
okay.
yeah. So yeah, exactly. So we say exactly. We explain the above. Yeah.
Yeah. No,
yeah.
I understand. Yeah.
Yeah.
Yeah, there was a question from the audience, and I would rephrase it. I think interesting part of the question is what general message can we take away from this line of work, and where are you heading? This is so borderline going into the offline questioning period, but like let's just finish with this question, and after that we really go into the offline case.
Yeah, but Chava, I guess the point to that question is from the reinforcement learning perspective. Message, right?
Right.
Not
Yeah.
it's a general message, but from reinforcement learning.
Yeah.
So I think maybe one of the points is that we've been doing reinforcement learning for decades, and it's called control theory. And there's so much that people have done, and there's so many really expressive problem settings that we've done. And I think that I wouldn't call necessarily the math in this low hanging fruit, but I would say that there are like a lot of things that we can learn that if we use like very simple principles with what's kind of come in the past, there are kind of really powerful problems that we can tackle. I think this speaks to I think that linear control is kind of an extreme case of RL, where basically being model-based is sort of the right thing to do. Linear control in a lot of ways is almost too nice because it's very homogeneous. You actually don't have to do exploration in linear control, and it's actually one of the unfortunate things about the setting. If I learn something in one region of the space, I know what it is everywhere because I have a homogeneous map. I think what's really exciting to me about kind of moving control more towards kind of exploration in RL is understanding how we get away from this linear setting. I think this work is important because we need to understand the linear setting and understand the limitations and the difficulties before we can move on. But I think a lot of my current work and my current interest is moving beyond the linear setting. So I'm going to plug a paper that's not yet on arXiv, but it's with my colleagues Zach Mamedi, Dylan Foster, John Langford, Sasha Rockland, Akshay Krishnamurti, Dipendra Misra, and Wen Sun, the whole Microsoft research team. And here we start moving beyond linearity by using nonlinear observation. Right now, I'm trying to understand model predictive control and understand what can we say theoretically. And I think what we're going to have to do is we're going to have to depart with the regret benchmark. I think learning theorists really like being optimal. Control theorists don't really care about being optimal because it's too hard to be optimal. And I think we're going to have to move to harder problems where we have to sacrifice some things we can say theoretically. But I think there's still interesting questions we can ask, like how much we degrade with nonlinearity, how much and what radius we can stabilize, other kinds of confidence intervals. So I think maybe the thing that excites me more is how do we actually pose kind of good performance for harder problems where regret is just kind of too hard to do. If we can understand
it's
that.
like multiplicative type of bounds that.
Yeah, multiplicative, or even not that, even just like I've stabilized a nonlinear system from data. How do I do that? Yeah, so but then
those questions have really been looked at in the control literature since for long, right? Like
I think so.
Really at the heart.
Yeah, but they're also kind of they're not written in the way that our community could be easily understood. I think we have like the non-asymptotic sample complexity perspective, the finite deviation balance perspective. I think we could try to understand that as well.
Yeah.
So that's where I see things going. Someone said this is a clever policy gradient algorithm. Yeah, I guess it is.
Nice.
Yeah.
Trying to translate it to the language of RL.
Yeah, that makes sense. So I mean, I think again for the RL people in the audience, the thing I want to stress is that exploration in linear control is really the control is much harder than the exploration. The exploration is sort of a trivial. Like when I said I don't know the system, that's an exploration part. In an RL paper, that would be the whole paper. In this paper, it's an extension, you just do least squares. So actually kind of bringing this stuff closer towards where I have to do hard exploration is pretty interesting.